For this week, we are going to have determining the domain and range of a function using its graph. This graph is an example of a constant function. We observe our domain from this point up to this. The domain consists of all real numbers greater than or equal to -5 but less than 6. So our domain is written as D equals the set of X such that X is greater than or equal to -5 but less than 6. In interval notation, the domain is from -5 to +6. For solid or closed circle, it is associated with bracket. For an open circle, it is associated with parentheses. And for negative or positive infinity, it is associated with parentheses. Observe this part of our graph. That tells us that the range is only restricted to 4 of all points as y coordinate. So our range is now written as a set of y such that y is equal to 4. Constant function is a linear function for which the range does not change no matter which member of the domain is used. This graph is an example of a linear function. So notice that our graph extends infinitely in both directions. Therefore, the domain is the set of all real numbers, and it is written as D equals the set of X such that X is an element of real numbers. In interval notation, it is from -infinity to +infinity. The range is also the set of real numbers. So R is equal to the set of Y such that Y is an element of real number. In interval notation, it is from -infinity to +infinity. Linear functions are those whose graph is a straight line. A linear function has the following form. Y, or f of x, is equal to ax plus b. Linear function has one independent variable and one dependent variable. The independent variable is x, and the dependent variable is y. We proceed to our next graph. This graph is an example of an absolute value function. Notice that the graph extends infinitely upward. Therefore, the domain is the set of all real numbers. So our domain is equal to the set of x such that x is an element of real numbers. For our interval notation, it is from -infinity to +infinity. The lowest point in the graph is at 0 and -2, and all points on the graph are above this point. So the range of the function is R equals the set of y such that y is greater than or equal to -2. The interval notation is from -2 to +infinity. Absolute value function is a function that contains an algebraic expression within absolute value symbols. So you have to recall that the absolute value of a number is its distance from zero on the number line. Our next graph is an example of a quadratic function. The graph extends infinitely downward. Therefore, the domain is a set of all real numbers. So the domain is equal to the set of x such that x is an element of real numbers. And in interval notation, it is from negative infinity to positive infinity. The highest point in the graph is at 3 and 4, and all points on the graph are below this point. We can now say that the range of this function is equal to the set of y such that y is less than or equal to positive 4. In interval notation, it is from negative infinity to positive 4. Quadratic function has a form y or f of x is equal to ax squared plus bx plus c, where a, b, and c are real numbers and a should not be equal to 0. Its graph is a curve called parabola. A parabola intersects its axis of symmetry at a point called the vertex of the parabola. So this is the vertex of the parabola. Our next graph is an example of a cubic function. Notice that the graph only moves horizontally from negative 2 to positive 2 with open circles on both ends. Thus, the domain uses a parenthesis, and it is from negative 2 to positive 2. Similarly, the graph also moves vertically from negative 2 to positive 2 with open circles on both ends. Thus, the range is from negative 2 to positive 2. Cubic function has either one or three real roots, which may not be distinct. All odd-degree polynomials have at least one real root. This graph is an example of a piecewise defined function. Notice horizontally that the graph extends infinitely downward, then went horizontally up to 0 and negative 1, and went infinity upward afterward. Thus, the domain is a set of real numbers. Through careful observation, you will conclude the same thing for the range. Piecewise defined function is defined not by a single equation, but by two or more. It is defined compositely using several expressions and different interval domains. Now let's proceed in determining the domain and range of a function algebraically. For our first example, we are going to determine the domain and range of the function f of x equals 7x minus 4. If you try to substitute values for x, you will always get a unique value for y. And this process can be done with infinite possible ordered pairs as a result. Thus, the domain and range are the set of real numbers, or in interval notation, it is from negative infinity to positive infinity. For our second example, we will determine the domain and range of the function f of x is equal to the quotient of the sum of 5x and 2 and the difference of x and 3. This is an example of a rational function. The denominator of rational function should not be equal to 0. Therefore, you have to equate the denominator to 0 to determine the excluded value or values. So we copy our denominator, which is x minus 3, then we equate it to 0. Now we isolate x by transposing negative 3 to the right side of the equation. So we now have x equals 0 plus 3. X therefore is equal to positive 3. Our x now should not be equal to positive 3. Since x is not equal to positive 3, the domain of the function is the set of real numbers except 3. Domain is equal to the set of x such that x is not equal to positive 3. To find the range of a rational function, you have to follow these steps. First, you need to replace f of x by y. So 5x equals the quotient of the sum of 5x and 2, and the difference of x and 3 is now written as y equals the quotient of the sum of 5x and 2 and the difference of x and 3. For our next step, we now solve for x in terms of y. We are going to use the multiplication property of equality or the cross multiplication. We now have y equals the quotient of the sum of 5x and 2 and the difference of x and 3 to be multiplied by the difference of x and 3. The difference of x and 3, which is to be multiplied to y, is equal to xy minus 3y. The difference of x and 3, which is to be multiplied to the quotient of the sum of 5x and 2 and the difference of x and 3, is equal to 5x plus 2. We now transpose negative 3y to the right side of the equation. And we also transpose 5x to the left side of the equation. So our equation is written as xy minus 5x is equal to 3y plus 2. We now get the factors of xy minus 5x. We can use common monomial factor. We factor out x because it is the common monomial factor of xy and negative 5x. And the other factor is the difference of y and 5. Then copying equals 3y plus 2. Now you isolate x by dividing both sides with y minus 5. x multiplied by the difference of y and 5 will now be divided by the difference of y and 5. And the sum of 3y and 2 will also be divided by the difference of y and 5. So x is now equal to the quotient of the sum of 3y and 2 and the difference of y and 5. For our third step, we are going to equate the resulting denominator to 0 to determine the excluded value or values. We copy our denominator, which is y minus 5, then equate it to 0. We transpose negative 5 to the right side of the equation. So we now have y equals 0 plus 5. So the value of y now is equal to positive 5. For the last step, we will now write the range. And our range is equal to the set of y such that y is not equal to 5.